Hello, in this video I'm going to review accelerometers as we apply them in this upcoming lab. And an overview here, just some things to keep in mind. Accelerometers, they're a sensor, but they're designed based on the concepts that we talked about in a related lecture on mass spring damper systems. And they're a sensor that's used to measure vibration level, usually the output voltage that's being measured being related to acceleration, typically in G's. So this sensitivity that's usually given for these instruments is usually reported, as I say here, in units of voltage out, often in millivolts per unit acceleration, usually reported in G's. The sensitivity varies with the frequency of the input. I want to talk very clearly about what the input is to the system, which is the motion that you're trying to measure. And what you'd like in a sensor is for the sensitivity to be constant over the range of frequencies that you might be measuring. And that useful range is usually reported as one of the specifications for these devices. So in discussing all of these concepts, keep in mind that they're related to the principles that you actually have probably covered in your system dynamics class. We're going to talk a little bit about what bandwidth means, for example, and try to relate it back to the types of things that you do in a class like that, which is the modeling and the analysis. Most importantly, I want to give you some level of comfort, confidence in using the devices and knowing why you do certain things with them. So in this slide, I show a figure that I showed in that lecture on mass spring damper systems. This is a nice little diagram that just illustrates the working, at least mechanical principles behind what we call seismic sensors. Accelerometers are a type of seismic sensor. They rely on the mass being an element that is acted upon when you move, in this case, the base. So this is a base-excited configuration, as discussed in that other lecture. The important thing to keep in mind is, that this mass is suspended from the case, within the case by a combination, and we model it, right, as a stiffness damper. It's not necessarily physically made with little springs and dampers, but it's usually this stiffness element is also what's being used to actually sense the acceleration. So it's important to keep in mind we're going to be talking about deflection of this spring. That deflection is what directly excites some type of fundamental sensing mechanism. And I want to show you a few of the most common types of sensing mechanisms, sensing elements that are used in accelerometers shortly. But remember, they work based on compressing those, and these could be different types of elements, materials, and so on. And we represent it by an ideal spring because it has some stiffness, and it may also have some damping, right? And actually, sometimes in accelerometers, they actually will intentionally put damping in there because you want to control the dynamic characteristics of these devices so they have favorable performance. And so you actually may put in, sometimes they fill them with fluid or other type of damping material in order to make them perform a certain way. And your understanding of mass spring damper systems, you understand how that, how you can control the damping level with that C here, or B is the damping coefficient. Okay, so before I begin discussing that, I want to show you, this is a page from a specification, or manufacturer specifications for the types of accelerometers that we're using in our lab. And these designations here are the different types of accelerometers. They're all different types. And I want to show you some of the specifications. And so when we begin talking about these, you'll see if you were going to go out and either use an accelerometer that exists or you want to select one, I want you to keep in mind at least the key specifications you have to use when you're trying to choose one. So input range here, right, here you go. Input range is important. Now that is the range of accelerations that you're interested in measuring. So the one that we have in the lab is this device right here. It's a CXL04LP. But note that the input range is plus and minus 4, and then the units G. In other words, these devices all in this column can handle acceleration inputs of plus or minus 4 Gs. Note 10, 25, 50. So up here you're getting into some high performance accelerometers. What that means, the more acceleration they can handle, it means that they're going to be less sensitive, right? In other words, the output's not going to be as high, but they're also going to be stiffer. You make them stiffer to protect the sensing element. So they're made to handle higher vibration, higher shock, for example. So the reason I chose this for the lab is because what we do in this instructional lab is learn how to use these. We don't want to excite them too heavily. We want to also see a response when we shake them lightly so that you can learn how to use them. But think about it, plus or minus 4G, that's nice kind of human scale vibration, and so that's why I kind of purposely chose these. There's other specs that are important. 0G drift means when you have no acceleration on there, what kind of change can you expect? That's a subtle one, but this is an important one. The sensitivity is, for other sensors that we've used in the lab, we always measure calibration or sensitivity. It's the ratio, and this is a note, millivolts per G. And note what it gives you is 500 or half a volt out, plus or minus 25 millivolts. So it's 0.5, right, millivolts per G output. So you excite this by 1 G, you'll see it change by half a volt. Okay, and the important thing is that this sensitivity, and I'm going to harp on this, and I'm going to show you how that arises in the analysis of the device and so on. This sensitivity is not necessarily constant with frequency. And what does that mean? Again, I'm going to get to that. Transverse sensitivity means if I'm looking at, remember, accelerometers are going to be sensitive in a certain axis because you're trying to pick up acceleration in typically X, Y, and Z, so in a triad. So the X, let's say the X direction accelerometer is going to be sensitive to X direction acceleration. But let's say this guy also had a little bit of Y motion. You only want to pick up the X. This tells you how much of that Y is going to corrupt that X output. So it's kind of like crosstalk in your device. So if I move in the Y direction, how much of that will show up in my X? And that's an error, right? So they want you to know what to expect there. So some of these you might not look at right away. It depends if they're important to your applications, but input range important, sensitivity is important, alignment error, bandwidth. I'm going to talk quite a bit about that, and that's an important one when you're choosing. And bandwidth is basically means what is the usable frequency range, and you hear the word bandwidth used a lot in many kinds of contexts, especially in communications. What's the bandwidth of a certain instrument? Obviously mobile phones and so on. But for us, and note the units of bandwidth is hertz frequency. This is cycles per second. And look at the units that they report. For our device, it goes from DC to 100 hertz. Okay. Do you know what it means when it says DC? Obviously, 100 hertz means 100 hertz, but what does DC mean? I want to explain that to you as soon as we start discussing this. Just so you know, when we talk about frequency at DC, it means basically constant. In other words, when we talk about vibration with a certain frequency, it means you're oscillating at a certain frequency. When you go to DC, it means frequency is 0. In other words, it's a constant acceleration. So this device that we have here is sensitive to a constant acceleration. A lot of accelerometers are not. This happens to be one type. So that's something to keep in mind in some applications that you might run into. Sometimes you need to measure that 0 frequency. You need to detect G, when you actually have a gravity constant gravity acceleration. Sorry, not necessarily constant gravity, but just constant acceleration. But it turns out gravity is a constant acceleration. So these accelerometers can actually detect, your g vector, which is kind of a nice feature to have. So those three are the three of the key specifications to think about. Shock is also important. How much shock can it take? Wow, this can take 2,000 Gs before you damage it. But by the way, it doesn't take a whole lot to put a really high shock into these devices, and then you basically destroy them. The other important things here: supply voltage. This runs off, a unipolar 5 volts, and this just tells you a little bit more. Also, this is another important one: the 0G output. Okay, what does that mean? When you have 0G output, that means if I have, what is the output on one of the axes when I don't have any acceleration on there, and it means what is the output voltage when you have no acceleration in a certain axis. So this tells you you're going to have 2.5 volts out of an axis of one of the channels. By the way, these are three. That's what the 3 means here. Is a 3-axis accelerometer. So the 3-axis accelerometer, each one will, if you didn't have any, if you had accelerometers sitting in space and there was no acceleration, 0 acceleration in all 3 axes, you'd see ideally 2.5 volts out of each channel, right? There's going to be 3 channels for these 3-axis accelerometers. And let me actually switch over and show you. Here's one of the packages. This is actually not the type that we're going to use. This is a single channel accelerometer. Notice they'll put an arrow on here, and this shows that this is sensitive in the direction of that arrow. Usually they'll have a serial number because they'll give you a specific calibration for it being tested, and that's the sensitive. This is a uni-axis accelerometer, right? So that's mounting, and it's sealed. This is the device that we'll use in the lab. See, it's a CXL04LP3 plus minus 4 Gs, and again it'll have a serial number on the side. It'll tell you the specific calibration that they might have performed. And note, it'll usually show for you the 3 axes. The one that you see here, you have this is the Y direction, X direction, and then up and down as the middle one here is Z. So Z, X, Y, right? And the output connections are fairly easy. In the lab, we've actually packaged this all up so you don't see any of this, but just so that you know, if you bought one of these, you'd have a connector of this type. You see over here on this side, you've got that little mark there. You see that? That little mark, that's the 1 pin. So typically, this has 1. So you have, 1, 2, 3, 4, 5 pins. Okay, on this connector. What are those 5 pins? Well, here's a specific for one of the accelerometers. There's a serial number. One of the accelerometers that we have in the lab. See here your X, Y, Z axes. Look, there's remember I mentioned the 0G voltage when there's no acceleration. What they measured when they calibrated this specific one back in 2005, this was the specific output where there was no acceleration. And here, look at the sensitivity for each channel, about half a volt, right? But these are the specific values. I have a posting on the course log. You can look up the specific accelerometer that you're using if you want the exact calibration. About half a volt is pretty good. But here's the 5 pins. Remember, pin 1 is you don't see the wires, but if you stripped it out to look at each of the wires, in case you didn't have that connector, if you had just the wire option, you'd see that you'd have a red, black, white, yellow, green, and you could see how you could hook these up. So these are really easy to use because you give it 5 volts DC, you connect the ground to the black, and then you've got 3 connectors X, Y, Z. Right. So we have three outputs on a connector box that we've hooked these up for. And then what they give on these are real simple calibration sheets. They tell you, oh look, the zero G voltage. What's that? That's the output voltage of the sensor when there's zero applied acceleration, right? So if you now, so think about this. Remember what the orientation of the accelerometer was with the z-axis. So let's say I held this guy here on Earth. So you have the X, Y, and then Z up and down, right? What would you read out of the Z channel in that case? If you have Z positive in the Z direction, sorry, and then you have a G acceleration pointing down, right? So that's going to give you a negative G in the Z direction, which means it's going to drop that 0 G voltage from, in this case, about 2.5 by about half. So it's going to drop it to 2 volts, right? So it's going to be sensitive to that G. So think about that when you're looking at your signals. Again, the sensitivity, all of these are reported in volts per G, right? So this is half a volt per G, or the way it's reported on that other page was 500. Look at these calibration sheets. Just take a quick look at them. Oh, this is kind of an interesting little note here on calibration. The simplest method of field calibration. So this means, hey, I've got this accelerometer out. I'm working with it, and I want to just see, is this working the way I expect it to? And this, let's just read this. It says the simplest method of field calibration is to record the sensor's output when exposed to the Earth's gravitational field, just the way I just mentioned. Expose the sensor to +1 G, right? That means you'd actually flip it over so that it's sensitive to +1 G to obtain a positive reading, then more positive than the 0 G voltage, just as I just said, and then expose it to -1 G to obtain a more negative reading than the 0 voltage, right? So what you're doing is checking the response to a DC. So that works well if you have a device like ours that responds to DC acceleration or constant acceleration. The way I learned that when I was learning to use accelerometers. So let's say, again, I have Z. The 0 means what? That it's actually positive down, right? So that actually is positive down. If I had an arrow, that would mean that positive, the positive was up. So it's positive down because you're looking at it from down this way. So the output from the z-axis should be reading the 2.5 volts, right? Plus, right? Positive G, so another half volt. So you would probably read 3 volts out of that, if I'm interpreting that correctly. So if I had this sitting this way, I have this hooked into my DAC system or measuring it with a multimeter, I'd see 3 volts. Then what you can do is you can just turn this guy around, and now you're reading a negative G, right? The way this test right here, where you just slowly flip it over, going from basically exposing this axis. So this axis, the positive axis, if you're reading the z-axis, and you take it from a positive 1G, right? You take it from a positive 1G, and then you convert that into a negative 1G. Think about that. You've changed it by how many G? By 2G, right? So the output voltage that you should see should change by the equivalent of a 2G excitation. So this is actually when you're in the field and you say, I'm going to check my accelerometer, hold it, flip it around. That's called a 2G test, right? It's a quick test on your accelerometer. Make sure it's close to what you expect it to be. And you should do that in the lab. Do your 2G test. You'll be reading, say, 3 volts. Do a 2G test. It should go to 2 volts, right? Because you're changing by 2G, by negative 2G. Okay, so do that 2G test. So that's that little calibration explanation there. The 2G test is a well-known kind of standard test. It's a good way to quickly check your accelerometer. So think about what I've given you there is probably enough to go into the lab and start working. I do want to just give you a little bit more on how these accelerometers operate. First, let's talk about some of the sensing mechanisms that are very common for accelerometers. We have studied strain gauges, which are piezoresistive. You can build a lot of the accelerometers you can buy out there are piezoresistive. Remember, those are kind of like strain gauge type. And these are made using microelectromechanical structures. The pressure transducer we used was piezoresistive. Strain gauge is embedded in a diaphragm. Here you have the equivalent of what's a small little beam with these kind of little hinges, and there's little gauges on here, little strain gauges that, and so this is your vibrating mass. You have a little stiffness built, with MEM structure. So you build a sort of a strain gauge like accelerometer, and these are very common. Think about how strain gauges are sensitive to constant forces. So these would also be good accelerometers for measuring constant acceleration. Okay. Many accelerometers that are coming out now are actually using capacitive type sensing elements. In past discussions on sensing in different labs, I've talked about resistive sensors. I've talked about inductive sensors, and the last piece really is the capacitive, which is also related to the piezoelectric. We've talked a little bit about piezoelectric, but the capacitive sensors are sensors that take advantage of changes in the capacitance. And in this case, you might have essentially two plates, and and remember what I mentioned when we started this discussion. When you have that mass moving and you have a spring-like element in there, what you want to detect is that change in that spring deflection, and a capacitive element is a really good way to do that. Then all you need to do is measure that capacitance, and you get a measure of the displacement, right? And that's what goes on in these sensors. So, capacitive sensors of all types take advantage of changes in permittivity, area, or the distance between the plates, and that's what these basic accelerometers do, right? So you can build capacitive sensors in a lot of different ways. So I wanted to just, I put this in here so that you can be aware of that. There's humidity sensors that are based on changes in permittivity, for example, and many sensors that take advantage of change in area or D or both. Okay. And here's just a slide that illustrates, you can have level sensors, pressure sensors that are capacitive, right? If this diaphragm gets closer, you have two plates, and you can sense pressure this way. And here's your accelerometer, right? You have two plates, you have a beam, compliance, mass, and you have your mass spring damper system, and you're measuring this distance. And here's your little humidity sensor. Okay. Now the sensor, actually the one that we use is technically this ADXL05, and that's been packaged as this Crossbow accelerometer, and it's a capacitive accelerometer. And just to show you the insides, this is a MEM structure. You have this beam here that's got some stiffness to it, and here's a center plate that moves between two plates. And effectively what's going on is when an acceleration is applied, so you see here an applied acceleration, the plates, the center plate here moves relative to these two, and you're measuring the relative capacitance, and that's how you can detect the acceleration, right? So that's again a measure of the displacement of the mass. Okay, so that's how a capacitive accelerometer works. Now, I've already talked about this, but I put this one single slide in here just to remind you that gravitational field applies a constant acceleration. So devices like the first two that we talked about, piezoresistive or capacitive, those are nice for sensing constant accelerations down to DC. Okay. Other accelerometers that are very common and are piezoelectric. Piezoelectrics use these piezoelectric type ceramics, crystals, and here it shows two different configurations. This shows that this is the mass here, the seismic mass, and there's a piezo element here, and that element is in shear. So when the mass moves, it shears that piezo element, and that causes what a piezo is it's piezoelectric means is as you shear it, a pressure or stress induces a change in the charge in that element, and you detect that change in charge. It's almost like a capacitive effect. So you detect that change in charge. But what happens with piezoelectrics is when you shear it, and if you hold it, like, so if you put a constant acceleration on there and you hold that shear, you talk about that charge kind of leaking out. If you don't hold it there, it's hard to hold it in there with a good circuit. You lose that charge, so you can't maintain the charge, and so it's not good at sensing constants that way. But it's very good at sensing dynamic change. So piezoelectrics tend to be very good at higher frequencies, very high frequencies. They can be very stiff also, so they're very good for measuring very, very high frequency. Whereas you might see these capacitive and piezo-resistives for lower frequency accelerometers. Okay, so high grade structural response, aircraft response, typically you'll see a lot of piezoelectric, much more expensive accelerometers than the type that we're using in the lab. Okay. And this happens to be from a company, Bruel Kjaer, a little schematic from one of their books. And just to show you, you can also build piezoelectrics, homemade. There's little sensors. You can buy little piezo elements, and if you shear this guy, and this shows you can put a little piezo element at the base of a beam, and you can build your own little accelerometer this way, and this costs you almost nothing. So this is also piezoelectric. So piezoelectrics don't have to be expensive. If you use these really cheap piezoelectric buzzer type elements, if you wanted to build something sort of homegrown. And there's a lot of accelerometers nowadays that you can buy off many websites like SparkFun, and I'll show you some. Very cheap, and they're a little bit more difficult to use. You have to build some instrumentation around them, but it's worth it if you're building devices on your own. Oh, and here's an excerpt from the sparkfun.com site. There are these little piezo vibration sensors. Look at this, $3 for a very nice. And what you have, this is a mass beam, and you have a little piezo film here. And these give really nice output. I've played around with some of these, and we've used them in the lab also, actually. But what you have to do is build a circuit signal conditioning to measure, because these are piezoelectric. They're not capacitive. So the piezoelectric sensors you need to have what's called a charge amplifier to measure the output of these. And so it makes for a nice little lab, but we're not going to do that in this lab, or we may not do that in this lab. Sometimes we do. We sort of will use this little low-cost sensor, and then we'll wrap it with some signal conditioning. So nice, again, look at that, $3 for a nice little accelerometer. These are nice for integrating into different types of products where you need to detect motion. And maybe you're not concerned so much about the exact acceleration, you just want to sense relative motions. These are good devices for doing that. Okay, so the key thing about an accelerometer is it responds to base motion, as I said, and it's also going to be sensitive to the frequency. So the ground motion, usually we start thinking about it as some displacement y that's got some magnitude, right, amplitude, and let's think of it as a sinusoid with some forcing frequency omega. Okay, we talked about mass spring damper systems that were unforced in a lecture on mass spring dampers. Here's an application where you have a forcing input, right? This is a base motion, and it's also a harmonic input. Okay, and by the way, accelerometers respond to all kinds of motion, random and so on, but it's easy enough to understand it just by thinking about it by frequency by frequency. And then what we do is compose an overall picture of what we call the frequency response. And when we talk about frequency response of a system, we talk about what does the output amplitude look like as I vary the frequency. Okay, so let's say I hold y constant and I sweep frequencies. What does that output look like at every frequency? That's the key part about accelerometers that you need to understand is when you talk about having a bandwidth of 100 hertz, like the accelerometer we're using, it means the sensitivity is going to be constant up until you get close to 100 hertz. After 100 hertz, it dies off. Okay, so that's a result of the fact that this system has a real response that has a limited bandwidth response. So the way to think about it is the output, and think of Z here, the sensitivity, call this G function, relates the deflection of the sensing element. So it could be, that piezoelectric, it could be the capacitor plates, it could be the beam, whatever element you're using. That deflection Z, right, is related to the input amplitude Y by this function G, and that G is the sensitivity. But remember, keep in mind that for all of these sensing elements, that deflection is typically a direct measure of eventually what is the output voltage. So if it was a strain gauge type accelerometer, the deflection of the beam would give you an output voltage. So Z is in a sense a measure of voltage. So what you have here is, think of Z, even though it's a displacement, directly proportional to the output voltage. So you have voltage proportional to displacement, right? So in fact, this function right here is not an accelerometer function because this is a displacement input. This in fact is more of what we call a seismometer relationship because it's measuring displacement. Turns out we can use this to help understand accelerometers as well, as I'll show you in a second. Now, I'm not going to go into great detail, but I want you to be aware that this function right here, you can derive these, and in fact, often in a systems course, you will derive frequency response functions from your transfer functions, and these are functions of frequency, and you get what we call amplitude functions of this sort. They basically just relate the two amplitudes of the output and the input, right? So what it means is if you put an input into a system that's a sine wave, for example, with a certain amplitude, what this function tells you is what is the amplitude of the output, because it's going to be at the same frequency, right? So that's what this amplitude and phase do. All you have to think about them is they just modify the amplitude, and in the context of a sensor, this function is important because that's your calibration constant. What makes it different from all the other, you recall all the other sensors that we've looked at, when we've done a calibration, we've plotted something like this, we'd say, oh, here's my output Y of interest, and here's my input X, or and this actually is my voltage, sorry. So that's your voltage output from your sensor. You might put in some variable force, whatever. Or the other way around when we do a calibration, right? We want X versus voltage, but you know what I'm talking about here. The output is a function of whatever that input is. And that sensitivity, usually we have some nice constant line, linear line, and that slope right there is some calibration constant. The key thing to think about when you have something like a dynamic sensor, like an accelerometer, is that K is not constant anymore. It can depend on frequency. That's the big difference. And that function comes from these magnitude functions, which you can derive. And I've included in here some slides that show that. I'm not going to spend a whole lot of time, but just to show you, for example, you can derive this. Sometimes you'll do this in a systems class where you'll start off with a differential equation and you'll derive what's called a frequency response function or transfer functions. That's where this comes from. So Z here is the displacement of that sensing element. What is it? How does it depend on Y? You can derive these, right, theoretically. And then you can relate, and this is how you do the design. You relate them to all of the critical parameters. Interestingly, right, to natural frequency and to damping in the device. I don't necessarily want you to spend a whole lot of time, but you need to be aware that it depends on damping and natural frequency. And it basically shapes what the sensitivity looks like. And I want to show you why that's important very quickly. I'm going to skip this slide, because you can plot these functions. And so look, see, this is a plot of Z over Y. This is a plot of this function gy, and you can see how it changes over frequency. And this is nice because it tells you, hey, if I'm in this region down here, this device, this is where I want to design my accelerometers. This is where I want to design my seismometers. So seismometers measure ground motion displacement, like you might use for earthquake detection and so on. Ground, if you were interested in how much the ground is actually moving, how much is the displacement changing? Whereas if I'm interested in acceleration, then I need to make sure that my device is designed so that I operate in this region, right? So that's how we use frequency response functions. Probably a little bit more than we have time for in this course, but you should have seen this in your systems class. And I'm just going to jump ahead, and I want you to see, again, a lot of analysis here, but bottom line is you can derive the accelerometer frequency response function, and you get this function here, which says how much does that, keep an eye, remember this is Z, is how much is that sensing element changing, right, as a function of acceleration. So this is your calibration constant, right, like for the actual accelerometer. This function here now is a function of omega, and when you plot that one, this is what I want you to see. It looks like this. It goes down to very low frequencies, and you want it to be flat. You want it to be constant up until a certain frequency, and then it starts rolling off because of the, remember, hopefully you've learned in your systems course that, you know, second order system usually starts off kind of flat, and maybe you get a resonance, and then it rolls off. That's what you're looking at here. So the natural frequency is what defines where your bandwidth is. Usually you operate your sensors way down here where it's hopefully flat. So a good sensor is going to be nice and flat here, and we talk about this region as the usable frequency. This is what that specification page has, right? DC, low frequencies up to 100 Hertz. And that's where this comes from. It all relates back to the physical parameters of your sensor. Okay. Just to show you some examples, here's the frequency, you know, the specification pages for the manufacturers. They'll give you these charts, and they expect that you know what this means. Oh, hey, look, the frequency response of this sensor that you're buying from us, it's got a flat, you can't see it, it's flat here, and it rolls off. It's exactly what we're talking. Let me just show you some other ones. Here's a calibration page from this is actually a piezoresistive accelerometer that we've used in the past from a company called Sensotech, which is actually now owned by Honeywell. This piezoresistive type transducer, look at the frequency response. From what we've talked about, whenever you see something like this, you should kind of, in your gut, know what that means. It means I've got a flat range here, and that's where I can use my accelerometer. And note that's about 100 Hertz there. It's kind of hard to see, but that's about 100 Hertz. This guy actually goes out to about 200 Hertz. So it's from low 50 to about 200. You have a pretty good bandwidth for using this accelerometer. A couple more. Basically, I'm just talking about here how, yes, I'm talking about the deflection Z, but the sensitivity of accelerometers is really in units of voltage per acceleration. I've kind of already said that a little bit, so I'm going to move on. So, bottom line is you want sensors, even though these good sensors avoid dynamics, you want that relationship calibration to be constant, but because of the way they're made, sometimes they have dynamic effects, but you want them to operate in these flat regions, where if you don't have a knowledge of how those flat regions are formed, then it's hard for you to kind of design them if you're doing that, or to know why you're selecting them. And that's really primarily what, at minimum, what I want you to understand about why bandwidth is an important specification. Just another one. Here's a piezoelectric. Look at the high frequency range on this guy. From 200 Hertz, it's flat. What they're saying here is below 200. You shouldn't trust it. In fact, piezoelectrics usually they'll roll off something like this. So there'll be a low frequency cutoff. Then there'll be a nice region where you can use them. This one you can use up to about 5,000, and then it's got a really sharp resonance in this sensor. So you absolutely do not want to use this accelerometer here. You want to use it only in the bandwidth, which is 200 to 1,000 to 5,000. Okay. Now back to our little accelerometer, right? I already talked about it. Now hopefully you understand the input range. What's the usable amplitude I can handle for plus or minus 4G. Beyond that, you're going to exceed the output voltage, right, from these sensors. And think about it. This gives you half a volt per G. So if you go 4G, it's going to go from 2.5 to 3, 3.5, 4, 4.5, right? So with 4G, you're almost at above 5 volts. You can't go above 5 volts on these sensors. So the full scale range is 0 to 5 volts. So so you have to stay within that input range. Here's the sensitivity. I talked about that already. Now you understand the importance of bandwidth, where it comes from. I probably gave you way more than you needed on that. And then you need to know what the 0G output is and what the output's going to be, and why is it at 2.5 volts? Well, it's because that's the center of operation. It goes from 0 to 5 volts, and at 0G, you're right at the center, 2.5. But if you put a constant G on there, it's going to drop it a half, so you're going to be biased to load it. And I'm done. So again, motion sensors of this type, displacement, acceleration, take advantage of basic mass spring damper configurations. A frequency response function is key. That's why this is a good lab actually to tie in when you're talking about transfer functions and frequency response functions, and I try to do that. The sensitivity is that function, and you should hopefully, if you had an opportunity to learn about frequency response in systems, you can see that the sensitivity is something that comes out of frequency response, and in that way it's related to the basic makeup of your device. It's related to the masses, the springs, and the dampers of these particular elements. We'd like the sensitivity to be constant over the range that we use it, and so that's why we say, use it only within the bandwidth. If you exceed the bandwidth, then you can't be guaranteed that you have just a nice constant. Like, it's not just half a volt per G anymore. It's in the dynamic range, and so all bets are off. You don't want to use your sensors in those regions. It's helpful to understand how an accelerometer responds both to amplitude and to the frequency of the input. Okay. All right. I hope that discussion also helps you on one of the pre-lab questions, which actually asks you to look at this specification on our particular accelerometer and to explain those and be prepared to use these sensors. All right. Thank you.